In this video, we are going to implement the pressure-driven pipe flow scenario with periodic boundary conditions such that we then see the Hagen-Poiseuille parabolic profile developing over the cross-section of the pipe. We will do that in Python in roughly 100 lines of code. So let's get started. Hi and welcome to this new video. The equations of fluid motion are creating such wonderful patterns in different scenarios. And here in this video, we want to look at the pipe flow, which is an interior flow scenario, so the flow through a pipe. And by the viscous effects of the Navier-Stokes equation, we will see this parabolic profile there. Interestingly, this is also one of these rare cases where we have an analytic solution to the Navier-Stokes equation, which also predicts this parabolic profile here. It is also named the Hagen-Poiseuille profile. And in this code that we're going to write, we are solving the Navier-Stokes equations. This is a system of equations consisting of a momentum equation. In 2 dimensions, it's an equation for both velocity components, and we have an incompressibility constraint, which is due to the fact that we are solving the incompressible Navier-Stokes equations here. The scenario we want to look at is the set pipe flow, which means that we have a rectangular domain where the top and the bottom edge are walls. Walls mean that we have a no-slip boundary condition that translates into the fact that both u and v, so the velocity components in x and y direction, are 0. And the left edge and the right edge are connected by the periodicity of the domain. So whatever flows out of the right edge re-enters from the left. You can also think of this as being a cutout from an infinitely long tube or infinitely long pipe. And now we will apply a constant pressure gradient, which is pointing to the left. So in other words, in the left, we would have a hypothetically higher pressure than on the right. And this is then forcing our flow within the pipe. Initially, we will start with a uniform profile, which means that at each point in the domain, we have a unit velocity in the x direction to the right and the 0 velocity in v or y direction. And then we get an expected outcome, which is this parabolic profile. So over time, we will reach a steady state, which means that it does not change anymore over time. And then we get this parabolic profile where we have the highest velocity right in the middle of our pipe. And we are slowly getting closer to a 0 velocity when we come closer to the wall. And this is because of the fact of the boundary layers that are created next to the wall. And these are created by the viscous effects in our Navier-Stokes equation and by the fact that the velocity at the wall has to be 0. So we kind of have this transition from full velocity to no velocity at all. And what we will also see is that we will conserve the mass flux. So we are not increasing the volume or mass flux that is going through our pipe, nor decreasing it. In other words, this means that in the beginning we had these arrows which were 1 long, but then once we have our profile, the middle arrow might be 2 long, 2 units long, and the arrows that are closer to the boundary are smaller than 1, so that on average we still have the same mass flow. Our numerical treatment will work as following. First, we can make the observation that the velocity in y direction, so not the one that's alongside the axis, but perpendicular to the longitudinal axis of our pipe, will always be 0. That is, of course, because the flow is just moving through the pipe, and since we are still in the laminar limits of our flow, we are not creating any turbulence, and it's just these laminar layers of flow moving through the pipe. And if a velocity is 0 throughout the entire domain, its derivatives will also be 0, which also means that it does not change over time and it will stay 0, so we don't have to consider it in our simulation. Then we can simplify the momentum equation. So if we look at the initial equation, this was an equation for both velocity components, but now we only have to consider one, so it simplifies in this kind of index notation that we have a temporal derivative, then we have our nonlinear convection or the self-advection, and then we have a convection term which would include the v velocity. Then we have our negative pressure gradient on the right hand side, as well as the diffusion term. And then by the observation that we made, this term will always be 0. So we only have to consider the nonlinear convection term. So this one is 0. And then the pressure gradient is constant and given over the domain, so we don't have to discretize anything here. And then for the two spatial derivatives that are left, which are the first derivative as well as the Laplace operator, which is the second derivative in x plus the second derivative in y direction, will be discretized by finite differences. And for this one, we will use a central differencing scheme, and here we will use the classical 5-point stencil of the Laplace equation. However, we have to take care that we are in this periodic domain, so we have to use a periodic version of both discretizations. And then we will do the following steps. First, we will instantiate the U solution, which is also the only primary unknown we're working with in this scenario. And we are initializing it with ones, so 1 unit velocity. And we're only setting the top and bottom boundary where the walls are, we're setting them to 0. Then we can compute the convection, which is done by this periodic central differencing scheme. You will see that. And then we do something similar for the diffusion with a periodic 5-point stencil. And then we can use an Euler discretization in time in order to advance our solution by saying the solution at the next time step is the solution at the previous time step plus the time step length multiplied with the collection of these terms here. And then we can enforce the wall boundary conditions, and we don't have to explicitly prescribe the periodic boundary conditions because they are already prescribed by using the periodic versions of our spatial derivatives or our approximations to the spatial derivatives. And then it's basically just a time loop, and we will repeat the process 1, 2, 3, 4 until we reach steady state. And this is then the Hagen-Poiseuille parabolic profile that we will see. And just a note, in comparison to other scenarios where we solve the Navier-Stokes equations, in particular the incompressible version, we don't have to solve for a pressure correction here. And that is because our pressure gradient is constant and prescribed throughout the domain. This makes this one of the simplest scenarios that you can numerically solve the Navier-Stokes equations in. And here I have some notes on the stability, but we will look at them later in the video. And then we can start coding. So I will go down here and start with the imports. And for our computations, we need NumPy. So import NumPy as NP. Then we need matplotlib. So import. And then I will also use tqdm as a simple progress meter. Then we can define some constants of our simulations. For this, let me go up and make a simplification. So here we said that we have a rectangular domain, but we can greatly simplify this by looking at a square domain. Because since we're using periodic boundary conditions anyways, it actually does not matter how many degrees of freedoms or nodes we are using in this x direction here. We could use 100, but 2 would also already be sufficient. For simplicity, let's just use as many discretization points in x as we have in y direction. So I will just call this the constant n points and say we're using 11 here. Then let's use a kinematic viscosity of 0.01 and a time step length of 0.2, and let's perform 100 time steps. Then we also have to define the prescribed pressure gradient. So I will do pressure gradient. And in order to remind yourself that the gradient in 2 dimensions is a 2-dimensional vector, I will also use a NumPy array here. And we have, that is what I want to use here, minus 1.0 in x direction and 0 in y direction. Because since we don't have any flow in y direction, and there is also no pressure gradient here. Of course, you could also just only save the -1 for the pressure gradient in x direction. Then let's scroll down a bit and create a main function. So define main and leave it empty. And then let's create a main switch such that our file is only executed with the Python interpreter. And then we can use the number of points in order to infer the length of an element, or you could also call that a cell. So I will just call this here element length. In other words, this is our spatial discretization length, so the dx. And here I will just use a domain which has 1.0 in its extent, for instance 1 meter, and then we divide it by the number of points minus 1. And that is, of course, if we have 11 points, then these 11 points make up 10 finite cells in the interior of the domain. And then we can discretize in x and y direction by saying x range is numpy.linspace from 0 to 1 with n points. And the y range will be similar. Here I will use 0 to 1 with n points. And just to remind you again that we could use only just 2 points in x direction, maybe 3 would be a little better, but that is sufficient because we're using these periodic boundary conditions. This is just a great simplification here. Then let's create our two-dimensional mesh, which consists of coordinates in x as well as coordinates in y direction, and we will use numpy.meshGrid, and we will feed it the x range and the y range. Before we start our time loop, let's define the discretized spatial derivatives. So first, let's do the central difference. So central difference in x periodic, so the periodic version here. And this one takes a field. So in our case, this will just be the u velocity. And then we have a differentiated field. For this, let us look at the algorithm. So here we were computing the convection and we are now implementing this operator. And it basically says that we are advancing our solution by one step in x direction. And we are advancing it reversely in x direction by one step. And this modulo n just ensures that we are re-entering in the beginning when we exit at the end. And there is a convenient operator in NumPy that does this for us, which is called roll. And we will use numpy.roll on the field with a shift of 1 in axis 1, which means we go one step forward in x direction, and then we subtract numpy.roll field shift, and now -1 to go backwards, and again axis equals 1 for the x direction. And if you ask yourself why we are using 1 and not 0, and that is due to the fact that we are indexing our domain in a form of a matrix. So you would consider, of course, that here this direction is the x direction, whereas the perpendicular axis alongside the cross section of our pipe is the y direction. But if you are thinking of your discretization as a matrix, then the y direction would be indexed as the rows and the x direction would be indexed as the columns, which is the reason why indexing x means that we are indexing at the second point, basically, or the axis is 1 and not 0. And then in order to get our derivative, we divide by 2 times the element length, which is due to our central difference approximation. And then we can return our differentiated object. Let's do something similar for the Laplace operator. So let's say define Laplace periodic, which also takes a field. And the differentiated object here is going to be given as, we will use numpy roll again. So first we roll forward of our field by 1 in x direction. Then we will roll forward by 1 in y direction. So shift again is 1, but now the axis is 0. And then we roll backwards one step using the field. Shift equals -1 and axis is 1. So x direction again. Plus numpy dot roll of our field. And again, we have a negative shift and the axis will be 0 because we are in y direction. And then we have to subtract 4 times the field itself, unrolled, so just indexed at the position that it is. And we divide this entire construction by the element length squared in order to get the 5-point stencil. And then we can return the differentiated object. And that's already all we have to do for our spatial derivatives. And then we can start with our time loop by saying for iteration in tqdm.range in time steps. And of course, before we can do something in our time loop, we have to define the initial condition. So I will call this define the initial condition. And here we said we want to use a once array for the velocity in x direction so that it is uniformly distributed over our domain. So we say velocity in x previous or prev, and previous means from the previous time step. And when we are in the 0th iteration, then previous of course refers to our initial condition. And this one will be given as numpy once and has the shape endpoints by endpoints, meaning it is endpoints in y direction and endpoints in x direction. And now we also have to set the boundary condition because it is not 1 on the wall boundary condition, rather it is 0. So we do velocity x previous, 0 and then colon, which means at point 0 in y direction, and the colon means all points in x direction. Let me show this to you in the plot here. So basically I'm now referring to this edge here. And this one of course shall be 0. So I just say equals 0, and then the same thing for the velocity in -1, which refers to the last element in y direction. Colon is also equal to 0. Okay, well then we can use this previous array in order to define convection and diffusion. So convection in x is going to be, let's look at our algorithm. So we said that the convection is approximated as the solution multiplied with the periodic central difference. So well, let's do that. The convection at x is the velocity in x previous element-wise multiplied with the central difference periodic on the velocity x previous. Then we have our diffusion in x, and for this one we will multiply the kinematic viscosity with the periodic Laplace operator applied to the velocity x previous. And then we can already go to our third step here to advance in time by using our explicit Euler step. And here we have to be a little bit careful about the signs. So because look at the original equation, we have to move the convection to the right hand side of the equation, so it will get a negative sign. So we have a contribution from the pressure gradient, which is negative. We have a positive contribution from the diffusion, and we have a negative contribution from the convection. So well, let's implement that and say velocity x next is going to be velocity x previous plus time step length multiplied with the negative pressure gradient, so minus pressure gradient. And since I used an array, I will index it at 0, which refers to the constant pressure gradient as it is distributed over the entire domain. Then plus the diffusion in x minus the convection in x. And let me move that to the next line. And this was step number 3. And now we can enforce the boundary condition. So we say velocity x next. And basically this will be doing the same as we had it here. So we say 0 in y direction and all components in x direction will be 0. And then velocity x next, last component in y direction and all components in x direction will be 0. And now we just have to swap basically the next with the previous, or just save the next as the previous because we are advancing in time. So I will call this advance in time. For this, the velocity x previous is going to be the velocity x next. And that's already our computation. Now we can interactively visualize our results. So for this, I will just say visualization. And for this, we will use a contour plot. I will use contour F here and say we have the coordinates in x, the coordinates in y, and then we want to plot a contour plot of the velocities in x direction. so that we see how the distribution of those are over the domain. And I want to use 50 levels in order to make that smooth. I will then activate the color bar to see what color refers to which velocity. And on top of that, I want to use a vector plot. So I will do quiver with coordinates in x, coordinates in y, and then we need u and v component of our velocity. So we have velocity x next. And since we know that the y velocity component will always be 0, I can just do numpy.zeros like velocity x next. And then let's add some labels. So I'll do plt.xLabel and say that is the position alongside the pipe, and plt.ylabel, which is the position perpendicular to the pipe, perpendicular to the pipe, maybe pipe axis to make it more precise. This is over the cross section of the pipe. And then we can interactively update our plot by doing plt.draw and then plt.pause for 0.05 seconds. And then we can plt.clf to clear the figure in order for it to be redrawn on the next iteration. And that should already be it. Let's open up a terminal and see if there are any bugs in our code such that we have to debug them. So I will do Python pressure-driven pipe flow, and this should then already compute. And here you see it works. So over time, you see that the velocities at the boundaries are getting smaller, or like the velocity arrows are getting tinier, and the ones in the center are getting larger. And we also see in the color distribution here that we have a higher velocity in the center, which is what we would expect for a parabolic profile. Let me improve the styling of this plot by using a dark mode, because the reason is why not. So plt.style.use a dark background. And maybe this helps us identify the features even better. So let me run that again. And now it's dark. And here we see in the beginning, we had this uniform profile with the color also being uniformly distributed. And now it's getting closer to this parabolic profile. And you also see the change that is happening in the color scale is getting smaller over time. That's because we are almost reaching our steady state. You could run the simulation for longer in order to fully reach the steady state, but I think that is sufficient here. What I now think is also interesting is to visualize the parabolic profile itself. For this, I will twin the y-axis. So I will just plot another plot, but which is using a different x-axis. So I will do plt.twin y direction. And there I want to plot the following. It might look a little strange in the beginning, because usually when you plot x over y, but here I'm plotting y over x, but you will see about that in a second. So we'll use velocity x next, indexed at all y position, and the first x position, which is actually the second because we have a 0 indexing. And then I will use the coordinates in y, indexed at all y positions, and then here also 1. And I want to use a white color here and use the x label, which is the flow velocity. And now if we run the simulation again, we see that we get this white line here, which starts in the beginning being really rather discontinuous, and then over time it's developing this parabolic profile here that you can see that kind of matches also the color that is indicating the flow velocity. And here again, you see that the change is getting smaller over time. I want to make one last addition here by adding an plt.show in the end, such that our last picture is not like thrown away, but it keeps running so that we can investigate it in more detail. And then I can run it again. And you see, well, in the beginning, as said, it was a flow shape that it has 0 at the boundary, and it was already 1. And now it is, kind of reaching this parabolic shape. And then you can play around with the parameters of the simulation. So for instance, you could decrease the kinematic viscosity and then run it again. which would yield that, first of all, it adapts the profile slower. That is because of the fact that the profile is based on the viscous effects of the Navier-Stokes equation. And when we have lower kinematic viscosity, our flow is less viscous, so the development of the boundary layer takes longer. And on the other hand, it also creates a smaller boundary layer because we have less viscous effects. So in case you remember it from the last one where we had 10 times as high kinematic viscosity, our parabola was way sharper, you could say. And this one is, not as sharp, so we have still higher velocities towards the boundary of the domain. And then, of course, you can also increase the kinematic viscosity, so to 0.1, for instance, and let it run. And then you see, oh, what is going on here? That is not looking right. And now we come to the stability part of our simulation, because here we use the simplest way we can approximate these kind of equations is using a forward in time, central in space for the convection and for the diffusion. And the explicit treatment of the diffusion is quite tough. So there is a stability constraint on the diffusion, which states that the kinematic viscosity times the time step length divided by the element length squared has to be smaller or equal than 1/2 in order for the scheme to be stable. And in that case that we're using here, this is no longer the case. Feel free to calculate the value and check for yourself. So here, in order to make that one stable, we have to decrease the time step. So I will use 0.02 now, and I think that should be sufficient. Yes. And here you see that we are now using a lower time step, but it is still developing the flow quicker. And that is, of course, because we have this high kinematic viscosity, which kind of results in a fast development of the boundary layer. And you also see the boundary layer is way wider than in the scenario with the 0.01. And that's quite a lot of things that you can do here. I will just reset it to the original one. You can play around with it. And also be careful that if you increase the number of points, you decrease the element size or the dx, which then in turn means that your system could become unstable or your simulation could become unstable. That's now the end of the video. I hope you enjoyed it. If you did, then please consider liking and subscribing. There are so many more videos like this on the channel, and I would be happy to see you also in these other videos. The source code file for the simulation can be found on the GitHub repo for the channel, and it's also linked down in the video description, so check it out, download it, feel free to play around. And even if you have an addition, then open up a pull request. I would be happy to see what you've done with the code. Here you now see similar videos and a playlist for the simulation scripts, and I would be happy to see you in the next video.